Ainitze Pol eta Ainitze. Then we do a joint presentation. So, stage is yours.
Thank you. Okay, so thank you everybody for coming. And today, Ainitze and I will talk and review a bunch of different methods, all of them to be able to measure or to detect the coupling constant between two electrons. And all of them, of course, are based on NV magnetometry. Now Ainitze will start.
All right. So our ultimate goal is to be able to detect or to determine the structure of complex molecules. A ver. Es que no sé muy bien cómo. ¿Así bien? Vale. So our goal is to determine the structure of complex molecules, such as, for example, proteins, and ideally also to be able to track molecular events, like, for example, the protein folding. Nowadays, the so-called protein folding problem is a research line which is very popular, and well, they study how a protein goes from an elongated conformation to a folded structure. The thing is that proteins, to success in their biological activities, they need to have a very specific three-dimensional structure. So the obtention of this particular structure is very important. And well, this is the research line where they study the mechanism in which the protein obtains this folded structure. And well, why it is important? Well, the thing is that genetic alterations, such as mutations, can alter this protein folding process and lead to misfolded proteins. And in fact, many diseases arise from this phenomena. So, well, it is interesting to learn about this process and also just the structural determination of different folded proteins. And this has many applications, obviously in biology and biochemistry, but also in medicine, for example, to develop treatments for this kind of diseases. And well, although it's important, the conventional techniques for molecular structure determination have some limitations. No? Like the most popular techniques are NMR and X-ray for structure determination. And well, the main limitation of NMR is that it requires large samples. And in the case of X-ray, it requires the crystallization of the samples. And well, the thing is that we want to study proteins or the different molecules in physiological conditions because that's where all the chemistry happens. And whenever we take these molecules to a few kelvins, different phenomena happens, or well, nothing happens at all. So these are the main limitations of the X-ray technique. And another popular technique because NMR and X-ray are for the characterization of the structure, and for the dynamics or to track molecular events, the most used technique is FRET, fluorescence resonance energy transfer, and this is based on tagging the target protein with some fluorophores, some reporters which emit light, and to track the movement of the protein basing of the emitted light. But this technique has a low signal-to-noise ratio, and well, in order to extract signal, it needs a long exposure, which implies that there is not good temporal resolution, and besides, it doesn't have also a good spatial resolution. So when it comes to the...
Would you comment something regarding AlphaFold, right? Because it's very popular, right? And it's
Yes.
actually related with protein folding. And yeah.
So, as I said, the protein folding or the research in the area of protein folding is very popular, and many groups are targeting this research by simulations or computational. They have a computational approach. And AlphaFold, for example, is a program where they calculate the structure of the folded proteins. So proteins are made of amino acids, and once AlphaFold receives the amino acids or a sequence, and it calculates which is the configuration that has the minimum energy with those given amino acids. And this is how AlphaFolds calculates the folded structure of the proteins. The thing is that it is proven that the minimization of the energy may not always lead to the perfect folded or the folded structure that the protein needs to achieve in order to be successful in its activity. Because in the cellular context or in the cellular environment, other phenomena, like, well, just to have other things around the protein that it's being folded, it affects the folding process. So it's not always the minimum structure that is the one that the protein needs to achieve to fulfill its biological activities. That's why it is important also to study the protein folding process itself in real life or in an experimental way, and not just based on programs that minimize the energy. So yes, okay. So I was talking about the limitations of conventional techniques.
So, okay, maybe one additional question. So, is AlphaFold is only for protein, not for general molecules or general big molecules?
No, I think it's only for proteins.
Yeah.
Okay, and AlphaFold uses machine learning to learn
Yes.
from the different data of them.
I
So
think so.
they have like millions of proteins and then learn the configuration and then apply it to a new protein.
I mean, I know it works with machine learning, but I do not really know much about it. I guess that they use different proteins and the information collected from the proteins that they already know how they fold. All right, so the MV magnetometry presents some benefits over these other techniques. And well, first, it is possible to carry out to probe a single molecule, which is not possible with classical NMR techniques. And besides, we are able to obtain a nanoscale resolution due to its small dimension of the MV. And we are able to make magnetometry at room temperature. And well, this obviously is a big benefit, because this is where the physiological events occur, and we are interested in studying these processes at these conditions. And besides, another benefit is that with the MVs we have a high fidelity initialization. This means that the MV can be initialized very easily with a laser. So yes, these are some of the benefits with the MV. And well, to track the movements of proteins, this is a possible scenario which was proposed by Carlos in the paper that he's publishing right now. And well, here we see a protein which is laying on top of a diamond surface, and this diamond has a shallow MV, which is located a few nanometers away from the surface. Besides, we have two labels on different sides of the protein. these are radicals, and in this case, they used nitroxides. And here in yellow, we have the electrons of these radicals. And the thing is that these electrons interact with the MV via a dipolar interaction, and besides, they do interact with each other also with a dipolar interaction. And the thing is that the strength of this interaction is given by G, which is what we call the dipolar coupling constant, and this G depends on the relative position and orientation of the labels. So if we are able to extract G, we will be able to track the movements of the protein itself. So this being said, our objective is to design protocols to extract G. All right, so, well, I have to mention that already exist experiments that prove that it is possible to receive the signal coming from an electron label located on a protein. This experiment was done in China by Faksan-Shi et al. Well, yeah, they were able to sense the signal coming from a label electron. They were able to measure the orientation and besides to sense the effect of the movement of the protein on the signal that they were recovering from the MV. So with this, we prove that what we are doing is, or that we are suggesting things that are feasible. Now I'm going to introduce the Hamiltonian.
Would you say that the protein embedded in this polylysine layer is physiological conditions? Because it's always embedded in some fluid or in some glass-like stuff, right?
They embed in this polylysine layer so that the protein doesn't move that much. And the thing is that this polylysine is it has a greater density than water, so it is not exactly physiological conditions because the physiological conditions would be when it is on water. But I think it is a good approximation of the physiological conditions.
Room temperature.
Yes, room temperature.
Okay.
Well, now, yes, I'm going to introduce the Hamiltonian. For that, I will present the different elements of our system. So as I said, we have the MV and the different label electrons. And then we have, in order to control the system, we have a radio frequency driving, which is able to control the spin states of the electron labels. And then we have a microwave radiation to control the MV. And besides, we have an external magnetic field. All right, so this is the Hamiltonian. And these right here are the drivings. As I said, this corresponds to the driving to control the MV. And this S is the spin operator of the MV. And similarly, this is the driving that controls the label electrons, and these are the spin operators of these electrons. All right.
N1 and 2 are the
N1 and 2
are the nuclear.
Yes, correspond to these labels. Now I will present what each one of these are. And so this other term is the Hamiltonian of the MV. The first term is the zero field splitting, and the second term is the Zeeman term, which comes with the external. When we apply the external magnetic field, we obtain this splitting between these two states. So when we set the frequency of our driving to match the energy gap between the zero state and the first state, we obtain an effective two-level system. And well, it is interesting to note that even this MV has like an electronic structure, this energy gap is not exactly of the dimension of that usually electrons have. It's slightly different. So this implies that with this driving, the other electrons that may be surrounding the system are not affected. With this driving, we have an individual addressing to the MV itself. Well, these are the Hamiltonians that correspond to the labels. And the thing is that we are interested on the electrons of the labels. But these electrons, the spin of these electrons is strongly coupled to the nuclear spin. So in the Hamiltonian, we need to take into account also the nuclear spin. So this is, as a consequence, we have a complex Hamiltonian. And well, these two terms correspond to the Zeeman splitting of the nuclear spin. This is the spin operator of the nitrogen, which is located in the nitroxide label. This is the quadrupolar moment. This is the term that relates, or that defines how the electron sees the magnetic signal coming from the label. And this is the interaction term between the nuclear spin and the electron spin. The thing is that this complex Hamiltonian can be approximated as this other expression, which is made in the paper published by Carlos. And well, this expression can be obtained by giving treating perturbatively the nuclear spin operators that are orthogonal to the external magnetic field, and that's why we are left with an spin operator which is aligned with the external magnetic field. And this other omega depends on the spin state of the nitrogen. This will have a value or another depending on the spin state of the nitrogen of the nitroxide label. And besides, it also depends on the orientation of the label with respect to this external magnetic field. So when we are targeting a label, we need to match the frequency, or approximately match the frequency of our driving with this omega. So this is what defines the energy scale that we need to match. And if we select different isotopes of nitrogen for each of the labels, which implies that we have a very different value on this omega, with the driving, and if we set the driving to match with one of the omegas of one of the labels, this driving will only affect this label. So we obtain an individual addressing, and we can forget about the Hamiltonian of the second label. And well, besides, it also would not affect the MV due to the same reason. The next term is the interaction between the label electrons and the MV, which is this also complicated expression, but invoking the rotating wave approximation, we get this other term because we can neglect the terms that go with Sx and Sy. And here, this A is the hyperfine vector, right here. Well, the thing is that we can approximate this expression with this other one. And similarly, with the interaction between the label electrons, we are left only with the Z component of the spin operators. And this G right here is the parameter that we are trying to extract. And we can see here how it depends on the relative distance between these two labels. So making all the approximations that I have been talking about, and besides moving to a rotating frame with respect to the Hamiltonian of the MV, we achieve this other interaction Hamiltonian, which is the one that we are going to be using during the whole presentation. So just to keep in mind, this is the interaction between the label electrons. This is the Hamiltonian of the label electron 1. This is the interaction between the MV and this label electron. We have the driving of the label electrons, and then we have the microwave driving. And now Paul will continue with the presentation.
Thank you. Okay, so now, after all of this, we know how our system behaves, more or less, approximately, like this Hamiltonian. So now let's introduce like the methods to detect this coupling constant G. So the first proposal is to use a pulsed sequence, meaning that we will be applying these two drivings to our system only during a period of time. And then for the rest of the time, we will let the system evolve freely. So during this free evolution time, the Hamiltonian would be this one right here without the drivings. And this free evolution time is actually the interesting one, because during this period, our system is like accumulating phase. And in the end, when we measure the MV, this accumulated phase, will traduce into the contrast that we will get in our measurement. So we are interested in having the longer free evolution time as possible. But apart from this, we have to take into account that we need to apply the drivings to our system, and that these drivings will have a certain duration, which will be determined by imposing that they have to act as pi pulses. Now, so the total time will be, well, the sum of this pi pulse plus the sum of the free evolution time. Now, in our simulations, we are not simulating yet the coherence, but we know that this effect exists. So what we can do is say, well, let's impose that the total time is, for instance, a relatively short duration, for instance, 6.5 microseconds. And then once this total time is fixed, notice how these two quantities are no longer independent. So once we set the duration of the pi pulse, the duration of the free evolution period will be also set, and thus the final contrast that we will get will be limited by this fact. Now, to avoid this kind of problem, there's another possibility, which is, instead of using this idea of using a pulsed sequence, use continuous driving, which means that we are going to be applying drivings to our system all the time, so that we will be accumulating phase all the time. Now, this seems to be better because we will accumulate more phase, but there's a counterpart, and that's that this coupling constant G that we in the end want to obtain comes or is harder to find when using these continuous drivings than when using this pulsed sequence. When using this method, it comes really naturally, while when using this, it's quite difficult to extract it, especially if we consider like errors in our measurements. All right, okay, we'll see this later, but now let's introduce this pulsed sequence in more detail. So we start again from the same Hamiltonian, and with working a little bit with this and going to some interaction pictures and taking some rotating waves approximations, we get to these conclusions over here. Now, this means that, or this tells us that if the second electron is in state 0, the effective Hamiltonian of the whole system will be this one right here, while if the second electron is in state 1, the effective Hamiltonian will be quite similar to the other one, to the first one. So notice how the effective Hamiltonian of the system depends on the state of the second electron. And apart from this, to obtain these effective Hamiltonians, we have to set these resonances over here for the frequency of our driving in radio frequency. So the first effective Hamiltonian will be true if the state of the second electron is this one, in 0, and if we set our frequency to be this value right here, while the second effective Hamiltonian will be true if this condition for the second electron is true and if this value for the frequency is also true. Okay, so what now? Well, usually electrons are not in state 1 or state 0, but normally they are in thermal state. So probably the second electron will find itself in a mixed state, combining the state 0 and state 1. So the effective Hamiltonian will be like a mix of these two Hamiltonians. Thus, in principle, if we scan in the frequency of the driving radio frequency, what we should see is that we should see this effective Hamiltonian when we match this value right here, and this effective Hamiltonian when we match this value right here. And what's the point with that? Well, notice how these Hamiltonians act on the MV. This is a sigma z operator, so if we start with our MV in the state plus, what will happen is that it will invert its population. So in the end, we should be able to by plotting the population state on the state plus of the MV, we should be able to see two peaks when matching these two frequencies. And if we simulate this, this is actually what we see. And notice how the difference between both resonances is actually the value that we are looking for, G. So if in the experiment we carry out this kind of analysis and we find these two peaks, the only thing that we need to do is measure the distance between two peaks, and this in principle should give us the value of the coupling constant that we're looking for. Yeah.
Which is the model you use to simulate that scenario?
You mean from which Hamiltonian
Yes.
we are simulating? Yeah. We are simulating from this Hamiltonian right here, but in an interaction picture with respect to this frequency, just to avoid throttlization and to make... All right. So this is, in principle, very, very nice and very, very clean. But of course, this model has some limitations. One of them is that in order to be able to see both peaks in our plot, we should set that the amplitude of our driving must not be larger than G, because we need sufficient resolution so that we are able to see both peaks and not only one peak. So this limits the maximum value of the amplitude of our driving. While in the other hand, this needs to be imposed. So this means more or less that the microwave amplitude must be much larger than the radio frequency, so that during the pulses nothing happens and only the drivings act. This means that during the pulses there's no interaction between the electrons. Now these limitations carry some problems, and that this one right here means that the pi pulse in radio frequency will probably be long. Now this means that, well, here if the pi pulse is in radio frequency is long, what we can do with the microwave pulse, because it will be shorter in principle, is apply, instead of one pi pulse, apply 2n+1 pi pulse, so that both pulses last the same. But the fact with having a long radio frequency pulse means, if you recall the relation with the times, it means that the duration of the pi pulse will be long, and thus the duration of the free evolution time will be small. This period will be short, and this means that we will accumulate a really little amount of phase, which in the end reduces to poor contrast when we do the plot that I just showed you, right? So now this plot right here, we have to say that apart from this, it includes the coherence, while in the other one that I showed you, we didn't, but we see that including the coherence, the contrast is really, really poor. Almost nothing happens. So this is one of the problems of this method. So let's see now what can we do to improve this. As I said, instead of applying a pulsed sequence, what if we apply the drivings during all the time? Well, we can do this, and starting again from the same Hamiltonian, because the system is the same, nothing changes. But now we keep in mind that the drivings are all the time on. All right, so from this Hamiltonian and working a little bit, we end up by being able to define some effective radio frequency driving. And that's because working a little bit with this expression, we are able to see that there's a component in the x direction, in the sigma x direction, and a component with the sigma z direction. So in the end, we can define an effective radio frequency driving in a new direction or a new axis, or actually two new axes. And yes, this allows us to define these two new directions where alpha and beta are the components of this new axis and are written in these ways. And notice how both of them depend on our coupling constant that in the end we want to detect. All right. These are mathematics, but if we define these new effective drivings, plus we set this resonance right here, so during this process, we need to set the amplitude of our microwave driving equal to this new amplitude of the effective driving. Right, so if this is true, the final effective Hamiltonian that we end up with is this one right here. And notice how this acts on the MV as before. So this, when this Hamiltonian is true, so when that resonance condition is met, the state of the MV will change if it's starting in the plus position. Okay, so the idea here is, so well, if we know that this Hamiltonian is true when this is met, what we can do is scan again on the amplitude for the microwave radiation, and we know that when this is true, this will be true, and thus we will be able to see again a peak on the population of the MV. And this is actually what happens when we simulate it. And again, with this position of the peak, we should be able, in principle, to obtain the value of G using this equation right here. But notice how before we only had to take the difference between the two peaks, which was quite easy. But now here, G is like more hidden and it's harder to obtain, especially if we consider errors to our measurements. But apart from this, notice how we obtained much more contrast than when using the, well, a bit more contrast than when we were using the pulsed sequence. So it's kind of an equilibrium between easy to obtain G, but poor contrast, harder to obtain G, but better contrast. So now here it all comes down to how errors behave. All right. Now, with this method, there's yet another possibility. And now, instead of scanning in the amplitude, we assume that we already are matching this value. And so we know for sure that our Hamiltonian will be this one. And what if now we let the system evolve for a certain time? Well, in principle, we should be able to see the Rabi oscillations following this Hamiltonian right here, and notice how the period of this Rabi oscillation will be related to this alpha coefficient right here, where alpha had this expression. So if we are able to measure the period, we will be able to measure alpha and again extract G from this measurement. And this is just so you can visualize visualize how this how this is possible. So the period will help us to find this G right here. And now Ainitze will finish the talk if I'm able to. Okay.
Okay, so in the pulse, I'm gonna remember some things that he said. In the pulse sequence, the difficulty was it arose from the contrast, right? Because we were not able to obtain an ideal contrast. And in the continuous driving schemes, we have trouble extracting G because it's hidden in a square root, so it is more complicated to extract it. And what the last method that Paul suggested, we were able to extract alpha and from there G. But what if instead of targeting alpha, we focus on beta? The thing is that beta is related to G a little bit differently, so we have G also on the numerator. So we think that it may be easier to extract G from beta. And for that, the first thing that came to our mind to obtain beta was to forget about the microwave driving. And well, the thing is that this is very easy to theoretically, but experimentally, if we do not apply any driving on the MV, the decoherence time falls drastically. But we are sure that exist other methods to extract beta, but well, just assume for now that we forget about the microwave driving, and if we do so, we obtain this other effective Hamiltonian where instead of alpha, we have a beta dependence right here. So this means that the period will depend on beta instead of alpha, and from there we can extract G. All right, so as Paul said, now in order to decide which of the methods that we suggest is the best, we need to carry out an error analysis. And well, we are looking forward to do this. We will actually go to Madrid in some days to learn about to treat errors with statistics and stuff. And well, besides, we need to learn how to apply decoherence in our simulations, because in the simulations that we carried out, we didn't take into account this phenomena, and it is important, and we need to see how this phenomena affects our methods. And besides, we are working on another scheme to extract G, which is based on the dangling bonds. The dangling bonds are some electrons that appear on the surface. And the thing is that usually these electrons are seen as enemies, and people, before doing any kind of experiment, they get rid out of them. But our idea is to use them as friends, as signal amplification antennas. No? So if we use these electrons, if we are able to use these electrons, it is equivalent to moving our sensors to the top of the surface, which is the best case that we are able to obtain, because we are closer from the labels, so the signal that receives this electron is stronger. Like, in fact, the coupling with this electron goes as the distance is -3, the distance -3. So if we make this distance, instead of with this one, talking with this one, we use this surface electron, and imagine that the distance we had before is now the half, the strength of the coupling increases 8 times. So it's 8 times greater. So this implies better contrast, and also the Rabi oscillation will have will last 8 times, will be 8 times shorter. So yes, this is the ideal scheme, and we are now thinking about protocols that we could be applying to this scheme to be able to extract the information using this dangling bond. So, well, this was everything, and thank you for your attention. Any questions or?
One question might not quite get that. Why are you focusing on beta, not alpha?
So we think that the errors will be smaller when we are extracting G from beta than when we are extracting G from alpha. Because in the case of alpha, we have G down here, and with beta, we have up here. So
that makes sense, I guess, when one analyzes this situation, but with errors and with a small precision, right? Because you always extract from this square root, it's complicated. In particular, when omega Rf is much higher than G. Right? However, in beta, it is linearly there, right? So that's when you introduce some deviations, that deviations appears in some way enhanced. You have to square and these things, which hidden the precision, right? And we are looking for precision here.
And also one question is that you are applying both the microwave and radio pulse, right? So your proposal is using continuous driving. And the formula is, if I'm not thinking, sorry. So if you're using continuous, like the interaction between the two pulses will become greater than like pulse sequence. So, I mean, what's the advantage for that? To limit the interaction between the two pulses, two drivings, sorry.
I don't know if I understood what you are asking, but in the pulse sequence, we are applying driving to the MV and the electron, right? And the thing is that in the pulse sequence, we do not want any interaction between the MV and the electrons during the pulse. So that's why we are setting this condition right here, where the microwave, this one. But in the continuous driving scheme, these amplitudes are similar to each other, so there is interaction between the MV and the label electrons during the driving. So we are accumulating the continuous phase, we are accumulating in the continuous scheme, we are accumulating phase during the whole process. I don't know.
Actually, I want to like say the coupling between the two drivings. I mean, if you're applying the continuous driving, the driving time will be much greater than pulse sequence, right? So they may cause like have a stronger coupling between the drivings.
You mean crosstalk effect? So
Yes,
okay, clearly. Yeah. So she's asking if, for example, the radio frequency over the electron radicals could affect the MV, and the microwave on the MV could affect the electron labels, because everything is there.
Okay, yes, that is. So the thing is that each driving affects only the things that we are targeting, and that is because we are setting the frequency of the drivings to match the energy gap, the exact energy gap in each of the cases, which they differ in both cases. So I don't know if you remember this thing that I said, where this omega defines the frequency that this driving needs to have, and this value differs from this other gap, this gap that the ND has. So yes, the frequency of the drivings are different, thus each of the driving affects only the things we are targeting.
And also one more little details. Can you go back to the page that you introduced your method about the pulse sequence? Yes,
This one.
yes. A little detail is that like you describing the drivings in the picture with red represent for microwave and blue represent for radio. And in the picture on the
Yeah, they are the other way around.
It's from the right, opposite color.
Oh yeah.
Yes.
Right.
Yeah, that's confusing.
Thanks.
Yeah. Well, should be the other way around.
Okay.
Yeah. Because at first I was a little bit confused. I cannot see the picture.
Yeah, you're right.
Okay, I have one question. When you are speaking about interaction Hamiltonian, you are never, well, don't take into account never the protein. The protein doesn't affect to the system because the driving you are applying is something that is tuned to interact with the electron of the target to the label, but there are electrons and the protein have tons of electrons. So it doesn't affect the electron is driving and all the noise that you have on the molecule that has tons of nuclei and this like NB cannot see all this noise or doesn't affect anything there.
We assume, I think, that the protein is paramagnetic, so that it doesn't have any important magnetic signal.
But the paramagnetism is the global nature of the molecule, but the individual elements are not going to be paramagnetic, no?
I don't know.
I'd say, but I'm not sure about it. So since we have free electrons in our labels, the coupling with them will be much stronger than with anything else. But I'm not sure if that's completely true because, well, for instance, the base of the molecule is probably much closer to the NB than these labels. But maybe I don't know. I'm trying to answer, but maybe when considering the coherence, we can like introduce this to the calculus. I'm not sure about it.
It's a good question. Yeah, because the point is that in some way you have something like a strongly coupled system, such as this electron, right? And it seems that the thing that this electron on the radical is watching more strongly is something which is a nearby nucleus, right? And we can describe that with Hamiltonian, which is unitary, and so on, right? Then you have to put other terms. Actually, these terms in some way gives to thermalization, right? These things has been already measured, right? Well, characterized and estimated, right? Then we have to put all the back there, right? So in these some Liouvilleans that in the end leads to some thermalization. Probably there enters mainly the motion, the interaction with the environment, and perhaps the interaction probably with the hydrogens of the label, and perhaps a little bit what you said. But it seems it's not the most important thing.
Okay, but what you said about the electrons, the important thing is that they are paired. So each electron is joined with another electron of the other spin sign. So it's like they are non-magnetic. That's the reason it's not paramagnetic.
And there's not free electrons in the molecule. They are always
Free electrons are like a quite weird thing in a molecule, and that's why these other molecules we are putting on them are special. They are radicals. So when you hear the word radical means an unpaired electron.
Yeah, because if there is free electron, you don't need radical.
In fact, you could directly see the protein. And this thing about the nucleus, I would say that's even another possible idea. Using the interaction of the nucleus in the protein, just to kind of see them through the radicals. But it's in the
So what you said, probably it should also appear even on the diamond, right? Because diamond has bonds, but it seems, well, apart, it is a stable substance, right? A stable matter, which means it is in a spin zero state. So no magnetic, no electric, right? And this has things.
And when you are speaking about like I don't remember how you say the word, but you say that the protein is like in a natural environment or something like this. I don't know how to call it, but it's that it has no. It's like more natural. You don't have to go to zero or everything. If you apply a magnetic field that is huge, it's not going to affect to the because you are when you start to speak say that this method is better because it's more in a natural stuff, it's more natural environment. You can see the process more in real life, like. But if you apply in a huge magnetic field, probably you are going to change the nature of how the protein moves and everything. No.
It's not huge, the magnetic field.
Yeah, because I think they have used alternative approach. So for modifying the magnetic field with the approximation. So in that case, it cannot be a huge magnetic field, I suppose.
Yeah. Also, apparently, right? So we are always looking for the magnetic field for this type of substances. Apparently, this does not affect the chemical reactivity, and this is what we are looking for, right? In some way, it only changes nuclear and electronic spin properties, and that does not affect well, as long as the whole community knows what the chemical.
Yeah.
So nowadays, actually, for really very high precision experiments in atoms trapped in very well isolated, it seems that the people is starting to believe that nuclear stuff could affect the chemical properties, but probably in a very highest order. But probably that cannot be seen here.
I think it's a known thing. I think it's typical to do it in a rate like the Oppenheimer approximation or something like this. Like the nuclear degrees of freedom are much lower than the electronic, so they do not affect each other.
Yes. Ah, okay.
In some way, what you said, it also supports this kind of development because NMR, one of the good things, very good things that minimally invasive. Apparently, it doesn't touch the properties, and that is one of the good things. Other techniques are more invasive, like crystallization and X-ray, and typically destroy it.
Thanks. Okay.
Good, guys. Very good.
Thank you.